Okay, so we have been looking at derivatives and starting to use derivatives to help us graph functions. And we were looking at before yesterday on how to find where a graph is increasing and decreasing by the first derivative test and finding critical numbers and testing on each side of those. And with the first derivative test and finding where it was increasing and decreasing, we could also tell where our relative extrema, local max or local mins, were occurring. And so the second derivative test tells us a little more about the shape of the graph and how fast or slow something is increasing or decreasing. And so we can find so the graph is either could be concave up or concave down. And the second derivative would tell us this. So in this section, you'll see how locating intervals on which the derivative is increasing or decreasing can be used to determine when a function is curving upwards or curving downwards. So notice there's these two different shapes below, and these here are concavity. And be careful, because when you're reading this and it says concave upward, if f prime is increasing. So that's not saying my function itself is necessarily increasing. It says my first derivative is increasing. So I wanted you to be aware of that. If it's concave up, it has this kind of shape like this. Let me see. Okay, so notice concave up, like in here, this is concave up, and it's decreasing function when it's concave up here, and it's increasing as it's concave up here. This was the original function. Concave down, your function is going to look like this. And so it's possible that your function's concave down and increasing and then decreasing. So things can change concavity in a graph. And so, for instance, you might have something that looks like this. And so if I was looking at this graph here that I just did, I can tell that this piece right in here that is coming from 0, probably has an asymptote. This piece in here, this is concave down until I reach about here. And I could find this interval by taking the second derivative. And this is going to occur when the second derivative is less than 0. It's a negative number. So notice that at this point, it starts to change concavity. So now it's not concave down anymore, it's concave up. And so we can find when our graph, our original function, is concave up by looking at the second derivative and finding out what intervals is that second derivative bigger than 0. And so notice it's changing from concave down to concave up, from less than 0 to greater than 0. So what do you think is happening at this point? So this point is called an inflection point. So an inflection point occurs when the graph of f of x changes concavity. So if I'm trying to locate this point on my original function, I'm going to have to find the second derivative, and I'm trying to find when is it changing from decreasing to increasing or increasing to decreasing with those values, or less than or greater than. And so this is when f prime of x is equal to 0 f double prime of x, the double derivative, is equal to 0. Or when it is undefined, and it meaning the double derivative. So just kind of like when we were doing increasing and decreasing, but with the first derivative, we also looked at when that was undefined. Well, I just wrote all that out, and look right below it, I have that all spelled out for you. So to test concavity, let f be the function whose second derivative exists on an open interval I. If the double derivative is greater than 0 for all x in that interval, then the graph is said to be concave up in that interval I. So if the double derivative of x is less than 0 for all the x in I, then we say it's concave down in that interval I. And then the guidelines, which I kind of stated while we were doing this, to determine concavity. So you're going to find when the second derivative, find the second derivative of the function. Then you're going to find when the second derivative is equal to 0 and undefined. They say make a sign chart. That's where I was doing our number line. And then you're going to determine, is it positive or negative? Choose values on each side of our critical or inflection point, critical numbers, and plug it into the derivative. Okay, so let me pull an example. Define coordinates of local and absolute extreme and inflection points, graph the function. So what if you had f of x is equal to x to the 5th minus 5x to the 4th? So let's use what we were just doing to graph this. And so it's helpful sometimes to figure out what the domain is. And if I look at this, I can tell because this is a polynomial, is all real numbers. So there's nothing I have to exclude here. I don't have any radicals. I don't have any variables in the denominator. I don't have any log functions. I think those are the things we have to worry about. And so looking at this, I need to figure out where it's increasing and decreasing. So we can figure out where it's increasing and decreasing by finding our first derivative. And so the derivative of x to the 5th is 5x to the 4th minus, and the derivative here, 5x to the 4th. So bringing my power down front, 5 times 4 is 20, x, and then cubed. So I notice again, this is defined everywhere. So I'm only worried about when this is equal to 0, and those are going to be my critical numbers. So we're going to find the critical numbers. And we're going to set that equal to 0. And I notice that I can factor that. And so when I set this equal to 0, I'm going to pull out a 5x cubed from both of those terms. And then I'll be left with a 1 minus 4. Wait, I would be left with a x minus 4. And so it's completely factored, set each factor equal to 0. I know 5x cubed is equal to 0 when x is equal to 0. And I know x minus 4 is equal to 0 when x is 4. And so now we want to find where it's increasing and decreasing. And so if we do our number line, you know what, it might be easier, and I usually don't do this. Let's do this. Let's make a chart. Maybe not. I don't know. Let's not. I can play with that later. Okay, let's do our number line. And 0 and 4, we want to test numbers on each side. So let's say x equals -1. And if we plug this back into the first derivative, this is equal to 5 times -1 to the 4th minus 20 times -1 cubed. I'm really only curious, is this positive or a negative number? I notice if I raise -1 to the 4th, that's positive. And I also notice if I raise -1 cubed, that's negative times the negative out front, which is positive. So adding two positives give me a positive, and so this is greater than 0. And so it tells me that on the left of 0, the graph is increasing. So choose something in between 0 and 4. So if we choose x equals 1, and we plug that back into the derivative, we get 5 times 1 raised to the 4th minus 20 times 1 cubed. I can see right away that that's going to be a negative number because this is 5 minus 20, which is less than 0. And so my function has to be decreasing between 0 and 4. And then choose one more number, so x equals 5. Plug it into the derivative. So we have 5 all times 5 to the 4th minus 20 all times 5 cubed. Okay. I think that's gonna be negative, isn't it? But let me just check. So 5 times 5 to the 4th, that's really 5 to the 5th power. Minus 20 times 5 cubed. Actually, that's positive, 625. So this is greater than 0. And so this is increasing here. Okay, so now that we know where it's increasing, decreasing, we can tell what our max and mins are. And so at x equals 0, I can tell we have a maximum point. I don't know what that max value is. I have to plug it back into the original. So we want to look at f of 0, and we want to look at f of 4. So plugging that into the original, that was x to the 5th minus, what was it, 5x to the 4th. So plugging in 0, well, that would just give me back 0. So we have 0, 0 is where a local max occurs. And so at 4, if we plugged in 4 wherever we saw an x, we would get 4 to the 5th minus 5 times 4 to the 4th. And so that gives us negative 256. And so we have a local min at 4, negative 256. So before we move on to the second derivative, sometimes it's easier if you just plot those points. Our scale is going to be pretty different because of the negative 256. And so we had x equals 0. That was a maximum point. And so we knew that it was going to be increasing here and then decreasing. I'm just going to kind of put a little note to myself. I don't know if that's the correct concavity. My guess is it is. But, and then at 4, so let's say 4 was here, we found that way down here at negative, was it 256? We had a minimum value. So it was decreasing till we hit that point, and then we changed direction and we went back up. And we increased from there on out. And so let's look at the second derivative. And we can find those values where we have inflection. Go grab the first derivative. Good enough. Okay, so that was the first derivative was 5x to the 4th minus 20x cubed. So second derivative, bringing our power down, this is going to give us 20x cubed minus 60x squared. And so we need to find when is f double prime of x equal to 0 or undefined. So again, it's a polynomial, so it's defined everywhere. I'm only looking at when is 20x cubed minus 60x squared equal to 0. We can factor out a 20x squared from both of those. And so we get x minus 3. So this is going to occur when x is 0. And when x is 3. To me, that's kind of weird. That it's occurring at our maximum, that it would change, excuse me, that it would change direction. That 3 makes sense to me. I just want to make sure I grabbed everything right. Okay, let's just carry on. So I found that these are possibly inflection points. I would have to show that what's going on each side. And so I have x equals 0, and I have x equals 3. And I'm going to plug in values into my second derivative. So choose something to the left of 0. And so if I chose -1 and I plugged it back into the second derivative, I'm really only curious, is it a positive or a negative number? I could figure out what the value is if I want. So I have -1 cubed, that's -20. -1 squared, that's positive -60. So this number is less than 0. And so that tells me that my function is concave down on the left of 0. My guess is that it's still concave down in between 0 and 3, because I don't think it changes concavity there, but let's check it. And so if we plug in the second derivative, let's plug in a number between 0 and 3. So how about x equals 2 or 1? And so if we plug this into the second derivative, what do we get? We get 20x cubed. So 20 times 1 cubed is positive 20 minus 60, which is still less than 0. And so this is still concave down in here. So that is not an inflection point at 0. Okay, so now choose a number that is bigger than 3. And so how about x equals 4? And so if we plug that into the second derivative, we have 20 times 4 to the third minus 60 times 4 squared. So if you plug those numbers in, my guess is this is a positive. So 4 cubed, that's 64, all times the 20 out front minus 60 times 4 squared, which is 16. That gives you 320. So this is bigger than 0. And so this is concave up. Okay, so what I thought was wrong, but wasn't wrong because of that was an inflection point. Okay, so concave down. At 3, we have an inflection point. And so we have to figure out what that value is, and you have to plug it back into the original equation. Okay, and the original equation was x to the 4th. So let's plug in 3 there. What was it? Minus 5x to the 4th. Actually, that was wrong. So this was to the 5th power. Original was to the 5th. Minus 4x to the 4th. So figuring that value out, 3 raised to the 5th minus 4 times 3 raised to the 4th. So that gives me negative 81. So back up here at 3, negative 81. Let's just change, we'll change it once we've gotten that. But so we said it was concave down, and this was a max. still concave down until we, at some point in here, change directions. And it's concave up from then on. Okay, so using where it's increasing, decreasing, finding max, mins, and concavity can help you figure out and look at the shape of the graph and what's going on there. So I don't know if you guys remember us watching that video, the 3 blue, 1 brown on the coronavirus, and how it was talking about leveling the curve or getting that inflection point to be 1. Oops, didn't mean to do that. Although it would have been the other direction, because we're increasing, unfortunately. Okay, so the other thing that's kind of cool is that the second derivative can also tell you if a point is a max or a min or not. And that's called the second derivative test. So let me try something. Why does it do it above? Okay. I don't like that it's above. Okay, so let's say, and this is called the second derivative test. For local extrema. Okay, so we're using the second derivative test to find out if a critical number is actually going to be a maximum or a minimum. And so what you want to do, so let's say let x equals c be a critical number of f of x. So if you plug that critical number in wherever you see an x in the second derivative, and you find that value is bigger than 0, that tells me it's concave down. Sorry, bigger than 0, concave up. So this tells me that this value at x equals c is a min. If you had plugged in that number into the second derivative and you saw that it was less than 0, then that tells me my graph is concave down. And this is going to be be careful, because I said is a min value, but it's really where a min occurs. So x equals c in this case is where a max occurs, because it's really the y value that they're looking for. Okay, if you plug it into the second derivative though, and you get back that that critical number is equal to 0, this test is inconclusive. So that just tells me that this test doesn't work, what I'm trying to find out, and I have to go back to the first derivative test and find out where it's increasing and decreasing. Okay, so let's look at an example of that. Identify coordinates of any local and absolute extreme points and inflection points. They give you this theorem, but they don't really give you any examples. So we can do this. Okay, what if we were given that y is equal to the square root of 3. Outside of that is the x minus 2 cosine of x. And you have 0 is less than or equal to x is less than or equal to pi, 2 pi. Okay, so again, direction says identify the coordinates of any local and absolute extreme points and inflection points. Graph the function. So looking at this, I noticed that I can plug any number in for x and not have any problems. Cosine, this trig function is defined everywhere for x. If I had a trig function where I have x in the denominator, like cotangent, tangent, secant, cosecant, then I have problems where it's undefined. But cosine and sine are defined everywhere in our domain, and it's defined everywhere here. I don't have x underneath the radical, and so I'm okay. And so I know my domain is all real numbers, and I can find out where it's increasing and decreasing by looking at the derivative. And so if I find the first derivative, well, the derivative of x is 1. And so this is just equal to the square root of 3 minus 2. And so times the derivative of cosine of x. And so the derivative of cosine of x, that one was negative sine x. So we have root 3. Well, negative 2 times negative sine x is positive 2 sine x. And so again, we need to look at when our derivative is equal to 0 and undefined. But same reasoning as with my original function, I can say that this is defined everywhere. And so I'm just worried about when is root 3 plus 2 sine x equal to 0. Oops. I really know that that's equal to 0 an infinite number of times, and that's kind of why they probably limited my domain in here between 0 and 2 pi. Okay, so looking at this, I need to get sine x by itself. And so I could subtract root 3 and then divide by 2. So if you're okay with that and me just jumping, this would give me sine x is equal to, we subtracted root 3, so minus root 3, and then divided by 2. And so we're looking at x values, which give us back negative root 3 over 2. Okay, so let's go back to trig. Let's think about when is sine x equal to positive root 3 over 2. So that is when x, I'm going to go think about degrees first, and then we can talk about radians. So sine x is positive root 3 over 2 at 60 degrees. But this is a negative, and so I have to think about which quadrants sine is negative. And so I know that x has to be contained in either quadrant 3 or 4. And so 60 degrees, that is pi thirds. If I take pi plus pi thirds, so that would tell me that x is 4 pi thirds. Or I can think of 2 pi minus pi thirds. It's been a little bit, I'm not teaching trig this semester. So this is 6 pi thirds minus 1 pi thirds, that's 5 pi thirds. And then we could think about any multiples of these. And so we actually have to be careful. I don't know if you remember, we're going from 0 to 2 pi. If I added 2 pi to these, this would get me past that interval, so I'm okay. So those are our critical numbers. So I could use the second derivative test. Let's use that because we just defined it to see if these are positive or, maximum or minimum values. And so I need to take the second derivative to do that. And so this was our first derivative. And so taking the second derivative. So square root of 3, the derivative of that is 0, and that goes away, plus 2 sine of x. So the derivative of sine of x, so we have 2 is cosine of x, positive. And so if we plug in our critical numbers, 4 pi thirds, and let's plug in 5 pi thirds, wherever we see an x there, and let's see if it's positive or negative. And so if we plug this in here, we have 2 cosine of 4 pi thirds. Okay, so that's pi thirds, which is 60 degrees. Cosine 60 degrees is 1/2, but it's in the third quadrant, so it's negative. So this is 2 times negative 1/2, which is negative 1. This is less than 0. And so this tells me that 4 pi thirds is a max. So x equals 4 pi thirds, a max occurs. And so if I look at plugging in the second derivative, 5 pi thirds to the second derivative, 2 times cosine of 5 pi thirds is equal to 2 times, well, pi thirds, it's 1/2. I'm in the fourth quadrant. Cosine is positive in the fourth quadrant. So this is equal to 1. It's greater than 0. And so I know that x equals 5 pi thirds. A min occurs. And so we can figure out what those values are, but we have to go back and we have to plug them back into the original equation. And so y was equal to, root 3x minus 2 cosine x. Root 3x minus 2 cosine x. So if I plug in the 4 pi thirds, It's not the prettiest number. Okay, so cosine of 4 pi thirds, that is -1/2. -1/2 times -2 gives me a +1. So this is √3 all times 4 pi. I'm going to move the 4 pi out front. So 4 pi √3 all over 3 minus, again, 2 times -1/2. So that is -2 times -1/2 is +1. If they ask for the exact value, well, that's 4 pi thirds. So 4 pi √3 all over 3 plus, I need a common denominator. I'm sorry. So let's just add this all in and make it a fraction. So 4 pi √3 plus 3 all over 3. To me, graphically, that doesn't mean anything without plugging that in the calculator. And if I had to graph it, I would have to do that. So 4 pi square √3 plus 3. So this is about 24.8, all divided by 3, which is about 8.3. So we have, that was a max of 8.3. So same idea, but now you're plugging in the 5 pi thirds. So you have √3 all times 5 pi thirds minus 2 cosine of 5 pi thirds. So cosine of 5 pi thirds, that was +1/2 times the -2 there. That makes this piece -1 over here. And this is 5 pi √3 all over 3. My common denominator, so that I could rewrite this as one fraction, is 5 pi √3 minus 3 all over 3. So 5 pi √3 minus 3, which is about 24.2 over 3, which is about 8.07. Okay, so that's not a very big difference between our max and our min value. That's where our min occurs. Or that's our min value. The min occurs at 5 pi thirds. So the question asked one more thing. It asked us to find the inflection points. And so to find the inflection points, we have to find when is the second derivative equal to 0. We found the second derivative already back in our work so that we could find if those critical points were a max and a min. And so let's look at our second derivative. Our second derivative was 2 cosine of x. So to find the inflection points, we're going to look at when the double derivative of y is equal to 0. And we found that was 2 cosine of x. equals 0. So if we divide both sides by 2, we're looking at when is cosine of x equal to 0? Well, cosine of x is equal to 0 on our y-axis, and so that would be when x is pi halves and 3 pi halves. And so we could test, these are only inflection points if it changes concavity on either side of these. And so we actually need to test to see if they're actually inflection points or not. There's an infinite number of things that make cosine of x equal to 0, but we are limited into our domain between 0 and 2 pi. So again, we're plugging this into our second derivative to see if it's true or false. If I plug in 0 into my second derivative, well, that would equal 2 times cosine of 0, which is 1. So this is equal to 2. And so this is greater than 0. And so this is greater than 0, it's concave up. And then choose a number in between pi halves and 3 pi halves. I would probably choose one that I know what cosine is. I know what cosine of pi is. Cosine of pi is in between there. Actually, will that tell me anything? What's wrong? So if we choose pi, just do it. Something's wrong. Oh wait, no, not sorry. I was thinking that it was 0 at pi cosine is, but it's not. So I have 2 cosine of pi. Well, cosine of pi is -1. And so this is 2 times -1, which is -2, which is less than 0. Since it's less than 0, it is concave down. One more value. So choose something to the right of 3 pi halves. I'm going to plug in 2 pi. And so I have 2 cosine of 2 pi. Well, cosine of 2 pi, that's 1. 1 times 2 is 2, which is bigger than 0, so this is concave up. So just kind of my reasoning why I knew something was wrong there when I was calculating cosine of pi wrong, because I was saying it was 0, which it wasn't. I knew that I found the only values between 0 and 2 pi that set it equal to 0. So how could I have an extra value which we didn't find before equal to 0? So I knew something was wrong, and a lot of times that's kind of helpful math when you're reasoning, you can kind of see or figure out where your error is. Okay, so we found that they are indeed changing concavity on each side of those critical numbers. So those are inflection points. Inflection points occur there, and you would just plug those back into the original equation. And so to find inflection points, you're looking at y of pi halves and y of 3 pi halves. And because I've already gone over time, I'll let you guys plug those in there, but we know that inflection points occur there, unless you want me to finish. We can go through that if you want me to. Okay, so let's